And welcome back. Quick refreshment break for everyone. I hope everyone at home took the time to take a few moments out, get themselves ready, because we've got a heavyweight now.
Now we're talking business.
Now
we're going racing.
Yeah, now we're going racing. So our next speaker is a guy by the name of Pat Wheeler, or I should say Professor Pat Wheeler, and he's got a long title, so I'm going to read it once properly, and I hope everyone appreciates. He is the Professor of Power Electronics Systems. He's the Head of Power Electronics Machines and Control Research Group, the Global Director of the Institute of Aerospace Technology. Now, what I read there is incredibly intelligent man. Smart man who knows a lot of things. So I'm excited to hear what Pat is going to talk to us about. And he is talking to us today about enabling technologies for transportation electrification. And I think that's key. What technologies can enable us to get to transportation electrification? Devon?
Yes.
Thoughts on your side?
Well, I can't wait to hear. We need to get to a space where we've got all these different products that work together in a city type environment. And now we need all the technologies and all the smart people in the world to kind of guide us to say, how do we get there?
100%.
Let's go.
Smart people like Pat Wheeler, hopefully.
Absolutely.
Done deal. Pat, are you with us, sir?
I'm certainly with you, yes. Thank you very much for that introduction. Not quite sure how to live up to that one, but we'll see how we get on.
Oh, fantastic, Pat. So, you and I met 2 years ago in Australia, and I was kind of blown away by all the stuff you spoke to me about. You've obviously got a long title. You're into a lot of very interesting things. I suppose from myself and Devon, let us get out the way and let's let the professor talk.
Okay, thank you very much for the introduction. I'm Pat Wheeler from the University of Nottingham in the UK. And I suppose in some ways I fit very well with the previous speaker, in that we're both advocates of electrification of transportation and what that means for our lives. I guess I'm coming at it from a different perspective. I'm coming at it from the technology end and what we need to develop to get to the point where we can do this. So just a little bit of background. As Rob just said, I'm the head of the Power Electronics Machines and Control Research Group. And one of the joys of being a professor is you have lots of people around you doing lots of really good work. So one thing to remember is all the things I'm presenting today, this is not all me. This is a team of 160 people working here in Nottingham in the UK. And we do a lot of technologies that are needed in transportation, a lot of technologies that are needed as we go forward in this space. And so, we do the electrical machines that you need for the propulsion. We do the power electronic systems. We need that for connecting renewables to the grid, but also for the motor drive systems that are going to drive these electrical motors and control them. And we need everything to be smaller, lighter, and cheaper, as well as more efficient. So we need to integrate things. And just as with the internal combustion engine, we need to manage the heat that is generated as losses within the system. So lots of different things going on, and we need to bring all these technologies together to make the dream happen. So I've put a couple of roadmaps in here. Just looking at what different industries think. And we've heard this morning and at the start of this afternoon about the automotive industry and where they're going. This is just one of the roadmaps that you can pull down and look at where we might be going over the next 30 years. And the first thing you see is that petrol, gasoline and diesel disappear over the next 15, 20 years. To be replaced with things that are going to be electrically driven, either as hybrids or all electric. Now, one thing I find fascinating about this particular roadmap is the fact that there's not one solution or two solutions as we have today. There's an energy mix in there, but you do see hydrogen, which will probably be electric propulsion and all electric propulsion, taking over half of the market. And I think that's important. I don't just work in automotive. I also do a lot of work in aerospace. And they have a similar problem in trying to bring down the emissions from aviation, particularly in terms of, well, in this example, CO2. And And they have some advantages. They can control the operations, the infrastructure, and so on. The big problem in the aviation industry is the time of investment. The aircraft going into service now will still be flying in 25, 30 years' time. And so some of this will already happen because the investment has already gone in. So if we don't take any action, then we're going to be at twice the year 2000 levels by 2050. Obviously not acceptable. The target by 2050 in aviation is to get to half the CO2 emissions that we have 20 years ago. So really to squeeze the way that they deal with that. We can argue whether that's enough or whether we should be going further. But as I say, the investment period in aviation is so long, it does take time to have these impacts. And the other thing there to note is that some of this is known technology. We've already done this work. But over half of these gains are in new technologies and new ways ahead. So that's a quick look into the future and where a couple of industries think we might be going and the time it takes them to get there. It's also worth looking back in the past. And we've heard a lot today about electric cars and the technologies that are available today. One thing that's worth remembering is this is not a new idea. The oldest electric car I can find relates back to 1828, almost 200 years ago. So the first cars were electric, and the peak of production was back in 1912, over 100 years ago. So actually, the concept of the car came from the electric car, not from the internal combustion engine. The problem we find though is that by the time we got to 1928, 100 years after the first recorded electric vehicle, all production of electric vehicles had ended. And it ended for two reasons. Electric cars were more expensive and people were concerned about the range of the electric vehicle. Unfortunately, those two things are things that we've still not solved as engineers and scientists. We're still working on reducing the cost. We're still working on increasing the range of electric vehicles. We're getting there, but we still have those fundamental problems. So it's interesting to reflect on what would have happened what would happen today if 100 years ago engineers had solved those two problems and electric vehicles had become the cars that we know and love over the last 100 years. That decision, those market-driven influences back in the early 1920s really did have a massive impact on the world, and something that we've now got to change. So what have we been doing? Well, at Nottingham, we do a lot of development of technology. We work with a lot of different industrial partners, but we also like to demonstrate what we do and to make it exciting and accessible. So I could talk about lots of research projects, lots of work that we do there. What I prefer to talk about is the electric superbike. It's a demonstration of the technology, but also a demonstration of advocacy of electric vehicles. So just to give you some ideas about this bike, it's capable of speeds up to 200 miles an hour. It has a peak power at the back wheel of about 200 kilowatts, so rather a lot more than your average car. Has about 25 kilowatt hours of stored energy, and it's faster around a Formula One track than a BMW Superbike. So this is not a slow vehicle. This is a fast vehicle. It's for racing, and it's been designed purely for racing. Why are we doing that? Well, the first reason we're doing this is because motorsport is a great way of making technology exciting and of raising awareness of that technology. TV and media coverage that we get from the bike has been fantastic, both from my university, but also to demonstrate how things can move forward. Race bikes can also be used to trial and test new technologies. this bike has a lot of technologies on it that have been developed, for example, for aerospace applications. We need things that are small, light and powerful on this bike. And so it's taking those technologies that have been developed in research projects and putting them in a very testing environment, a very harsh environment. When you race a motorbike, you tend to drive that motorbike to its very limits, something you tend not to do with your family car too often. So it really does allow us to take more technological risks and find the practical limits, find out what fails. If you're racing and something fails on a bike or a car, you put it down to experience and you learn from it. It's a little bit different when you're producing millions of cars. You don't want to find those practical limits in that environment. And we're also testing and challenging new ideas. So one of our favorite races and where this bike was designed to operate was at the Isle of Man. So I'm just doing a little bit of geography. The Isle of Man is a small island between England and Northern Ireland. It sits out in the Irish Sea. It looks like it's part of the United Kingdom. In fact, it's a self-governing island. It has its own government, it has its own laws, and it has its own rules. So every year for 2 weeks, they close the main roads on the island and we go and we race motorbikes around it. Happened for over 100 years, racing motorbikes around this particular route. And this route is 38 miles, about 60 kilometers long, and it's on small country roads. It is not a normal racetrack. This is doing what every motorbike owner dreams of doing, testing their machine out on real roads, past houses, over hills and so on, and really racing in an environment that you would normally ride in. So we've done quite well there. We've been racing against teams like Honda, and we've been coming second and third, so finishing on the podium 3 out of the last 5 years. Great for publicity. You may recognise Prince William in the photographs on the right-hand side. He was there in 2018, taking a lot of interest in our team and chatting to the members of our team and so on. So really raising the publicity levels that we get, as well as being a great place to try this out. So what's enabling this? Well, when we look at any drive system on an electric vehicle, you need some energy storage. So if it's all electric, that would be a battery pack, exactly what we have on the motorbike. We have some power electronics, the thing that I'm professor of, that's the blue box on the screen there. And we have an electric motor, the orange square on that screen. In the electric motorbike, there's no gearbox. It's a direct drive from the motor to the rear wheel, single speed sprocket. As the previous speaker was saying, electric vehicles are really torquey. You get instant acceleration. The controller is going to respond in microseconds to any demand that goes in there. So that motor is very torquey and very capable of accelerating the bike without the use of a gearbox. So no wasted time changing gears or anything like that. The bike will accelerate quite rapidly without that. So these are the elements we're talking about. And so to do this and to enable electric vehicles to happen, to increase the performance, increase the range, increase the efficiency, we need to look at these elements that we have on here: the battery, the energy storage, the motor drive, power converter, and the electrical machine itself, and get the performance of these we need. This is great in racing because we're being pushed by our competitors all the time, but it's those technological developments that then go into the everyday electric vehicles, maybe scaled down a bit, maybe in larger vehicles. So the sorts of powers we're talking about here might be what you would need in a truck on a normal road. So great way to demonstrate that technology and get the efficiencies up, get the range up, and so on. So when we're looking at this, we've done a lot of work on the electrical motors themselves, how to make those smaller, lighter, how to use the new technologies that are coming along in terms of integration, magnetic components, all the great things that professors like to spend a lot of time working on, and where we do a lot of our research to try and improve these machines. Now, what you can't do for an electric vehicle is go and buy an off-the-shelf motor that's been designed for a different application and use that in the electric vehicle application. What you need to do is to design, build your electrical motor around the use cases that that vehicle would expect to see. In the electric superbike, this is really easy. We know how a number of riders will ride our bike around that track, around the Isle of Man TT course. We know that that's how they're going to ride the bike. We know what the duty cycles look like. We know exactly what that use case is all about. So we can define that really well and optimize the electrical machine just for that race. Now, that's a little bit harder when it comes to cars for everybody else, or trucks. There's a range of use cases. We don't all use cars in the same way. A taxi is driven in different duty cycles to, say, somebody who uses their car to tow trailers and to drive across the country. But we can take those ranges and optimize the electrical machines and the drives around that. We need to be able to control that electrical motor, and this is the big step forward that they didn't have in the 1920s. So when they first had electrical cars, they didn't have controllers to control the electrical motors using power electronics in the way we do today. There isn't just one design of power electronic converter you would use in this application. There's lots of different designs, there's lots of different topologies of those power electronic converters, lots of different materials that are emerging that we can use for the switching devices we need in those power converters. And they have some great advantages that we can use. So here is just showing the efficiency gains that we're having by going from silicon-based switching devices to silicon carbide-based switching devices. Devices that were just not available 10 years ago, but now are allowing us to get massive increases in the efficiency. Why is that important? Well, that reduces the losses in the vehicle, so you don't have to take quite so much energy from the grid. You can drive your vehicle a little bit further for every full charge of battery that you put in there. So all those things work really well and are pushing towards removing the problems of range, reducing the problems of how long it takes to charge the vehicle, reducing the weight of the vehicle and the amount of energy you waste in driving. So, and a good example there of where at the very small level, these devices are only 2 or 3 millimeters square, but where that technology in the switching devices, very small level, is helping us to develop the power electronic converters we need to enable more practical electric vehicles. All very important in terms of moving forward. And we see this this graph here is just showing the different devices, silicon and silicon carbide, and how they affect the size and the weight of the power converter, in this case in terms of the volume of the filtering we require there. So again, an example of how the volume in this case of that power converter is coming down. This means that your vehicle is a little bit smaller, slightly more room for your luggage and your people, making that vehicle more practical, making it lighter, and so on. So that's the electrical machine and the power electronics. The other problem we have is with energy storage. Gasoline, petrol, or diesel are both very good in terms of the weight and volume to the amount of energy you have. And they also, in a vehicle, have the interesting effect of reducing the weight of the vehicle as you drive. With a battery, the battery stays almost exactly the same weight for the entire journey. It doesn't matter about its state of charge. The battery will always weigh the same. This is interesting for the motorbike because it means the dynamics of the motorbike are constant throughout a race. something our rider noticed quite quickly. What we're waiting for here, I guess, is that at the moment we are reliant on lithium-based batteries. They give us the best volumetric and gravimetric energy densities, so they give us the lightest, smallest solutions we can use today. If you look at the history of rechargeable batteries, we find the chemistry keeps changing. We still have lead acid batteries in our cars for the 12 or 24 volt systems that run the auxiliaries on our everyday cars today. But it's quite an old technology, and most of us will probably remember going through NiCad batteries, nickel metal hydride rechargeable batteries, and then the lithium-based technology came along. If you put a time axis on that graph in the top right hand corner there, you would find that we're overdue a change in chemistry. There should be something else. And interestingly, when we do get that next change in chemistry, a number of interesting things will happen. You'll be plugging in your telephone once a week to charge it rather than once a day. And the whole problem with the range of electric vehicles will go away, because the weight and the size of the battery we need will be at the point where it's no longer something that's an issue. So that'll be great to see, that battery getting smaller, that battery getting lighter. It's practical today. The previous speaker was mentioning the Vidian trucks with a range of 500 miles. I don't know about anybody else, but I need a cup of tea or coffee before I drive much further than that. But there's still that anxiety there. There's still the cost factor there. And hopefully what we'll see is another chemistry coming along and that disappearing in time. So lithium-based batteries make electric vehicles feasible. The next chemistry will make them hopefully irresistible to everyone in terms of what we're doing. Just to explain the last bullet point on this slide, when we're racing electric motorbikes, we don't care about the lifetime of the battery pack. And to a certain extent, we don't care about the cost. We're looking to win races. And if you're looking to win races, you need to push the technology as hard as you can. So it's been a great way to test battery technology to the very limit. So what have we learned from racing electric superbikes? Well, we've learned that racing is a great way to enthuse people and to generate impact from the technology, to demonstrate that technology. We've discovered that electric racing is still possible to compete at the highest level, even though we're a very small race team, but we do have all this research background we can bring into to play. Simulation has been great in predicting the performance of electric vehicles, and that's something we've taken on into predicting the performance of planes, of cars, trucks, buses, and so on. But also there's a lot of development that will still continue to happen. We're still trying to solve those problems of over 100 years ago of cost and range, and we're getting there. We're still not actually ahead of the internal combustion engine yet. So as the previous speaker was saying, part of the electrification revolution is going to be about the advocacy, about government intervention, and about doing the right thing for the planet. It's not all going to be about cost and how we've got to change the way people feel. Now, we do a lot of work at Nottingham in aerospace. I'm not going to go into that, but just to say that as well as demonstrating road transport, we also do a lot of work in demonstrating what will happen in aviation. It's always good to have an equivalent of the motorbike, but for flying. And we don't just race motorbikes, we're also developing the electrical systems to allow aircraft to race. So this green aeroplane you see in our lab, in that photograph, is a small race aircraft. It used to race in Air Race, which is a the Formula One of single-seater aircraft, racing around pylons, either tip-to-tip or time trialing. And we've taken the electrical system concepts from the motorbike and we've installed those into that aircraft. So that aircraft will be able to fly, be able to race with an electrical motor and an electrical power system. We're doing that to get through some of the problems, to develop some of the ideas and the technologies that are needed, and to demonstrate those on a small scale, yes, but in an exciting aircraft format. And alongside that, of course, is all the work we're doing on trying to take that technology and apply it in regional and large civil aircraft over the next 20 to 30 years as this technology develops. So my conclusions from all of this is really to say that electrification of transportation, it is happening today. We need to continue that technological development as the rollout of electric vehicles, planes, trucks, cars continues. Power electronics and electrical machines are a key technology to enable that to happen. They have to be efficient, they have to be light, they have to have a reduced cost, but also the energy storage systems, the batteries, do need to improve if we're going to increase the range and the purchase costs. And finally, because it's topical, COVID-19 has caused a blip in demand. We heard about that earlier. But in terms of the roadmaps that we're looking at here, it's shown what is possible in terms of emissions, but it's not significant in affecting this move to electrification. I believe we're going into a 5-minute break next. What you'll see in that 5-minute break in terms of a video is actually 2 electric motorbikes. One is the one you see in this picture, the University of Nottingham team, which had a camera on it, and being followed by another bike. And so you'll see these 2 bikes racing literally shoulder to shoulder on the Isle of Man TT, just showing how exciting it can be to have electric vehicles. Back to you, Rob.
Fantastic, Pat. I mean, it's really exciting to hear that you've simplified, I think, a very complex system for everyone so that the layman on the road, on the street can understand. And I'm really excited to see this video of the Isle of Man TT. I think for any rider to get on board an electric rocket around the Isle of Man takes quite a lot of guts and courage. So I'm excited to see what the video you got to share with us.
Yeah. Wow.
That's just exciting. To see that torque and acceleration. I mean, he passed a few of those other guys like they were standing still. I mean, what a way to test the technology. What a way to find the breaking point and find where the limits are.
Yeah. Racing improves the breed, definitely. Thanks, Pat.
So Pat, I think that that's been super exciting to see, and I think that you've touched on a couple of things which are really interesting. You touched on aviation a little bit, and we instantaneously got a question straight away. Someone said to us, "Could you give us a little bit of a rundown on what is the status of electrification in aviation?" I know we're here talking about EVs, but people are obviously interested in what is the state of electric aviation in your opinion? Maybe a quick summary where you think it is at.
Yeah, I could give you I could give you a similar talk about where we are in aviation, and certainly those are things we do. So for the aviation industry, there are various demonstrators, and I showed you the one we happen to have at the University of Nottingham. But there's lots of single-seater and two-seater demonstrators out there today. Small electric motors, limited time flight, maybe up to an hour or so, and people looking at challenges. Can we fly from the UK to Australia? Can we fly a small aircraft across the oceans and so on? So really going back actually to the exciting days of aviation when people first started doing those kind of journeys in conventional aircraft. But also what's happening is lots of work on hybrid aircraft. Can we use electric motors to boost the existing engines? And the reason you might want to do that is because that reduces the size of the gas turbine by removing the peaks, and therefore increases the efficiency of your aircraft. So you can get some really good short-term, quite quick, reductions in the use of fossil fuels in aviation just by putting in some what you might think of as a mild hybrid system. When you go on from that, the next stage is to have full electric propulsion, so to have fans on the wings of the aircraft rather than jet engines. And then if you want to go a longish distance, the problem you have is that the batteries are still too big and heavy to give you a good range. If you have duty cycles which are short distance, maybe up to an hour, then that becomes possible. But when you go over an hour or so of flight, you soon realize that aviation fuel is very useful. But you can imagine an aircraft where the gas turbine is in line with the passengers, so not in the airflow of the aircraft. It's operated at its optimum speed and optimum power point at all times, and then you use smaller, lighter electric fans on the wing to actually provide the propulsion. And that's probably the next level of hybridization that people will go to. Then people are looking at hydrogen, either as a fuel for an engine to run a generator, because when you burn hydrogen you just get water, or to use it in a fuel cell to generate electricity and to power the aircraft that way. And then hopefully in time we will have the electric batteries that we can store the electrical energy in the weight and the volume that's needed to have an all-electric aircraft that runs in exactly the same way as an EV or indeed the motorbike. So I see that as a sort of path that we will have towards electrification. And the developments you need for the electrical motors, the power electronics, the electrical systems, that's all happening today. But the one problem with aerospace is that the time for development to getting it on an aircraft and flying is quite a lot longer than the turnaround of a new product in the automotive industry. So it will take time. Sorry, that was a very long answer to a very good question, but
no, well, I mean, it's fantastic. I think giving us a good bit of context. Devon, I know you've also got a question on our Facebook feed that you've picked up.
Yes, absolutely. Do you really believe that electric cars will make a real difference in CO2 reduction in the next 10 years?
I'm probably not the best person to ask that question of, but I think that mix is going to change, and certainly, in some areas of the world, that will make a massive difference. If you imagine a city centre only having only allowing electric vehicles into that city centre, you can suddenly imagine how that is going to clean emissions locally. But so you will see some very big benefits very quickly.
Good.
So there's measures like that, I think, will be the things that we first notice. And remember, it's not all just pollution. It will make city centres quieter as well. Really improving the environment in a number of different ways. It will take longer to have that impact at a global level. I'd be the first to agree with that. But if you don't start, you'll never get to the end point.
100%.
100%.
I think that's great. Now, you touched on it, Pat, and you spoke about batteries and the chemistry, and how we overcome range anxiety by having batteries that are smaller and can go further. And obviously, you triggered a flurry. I mean, we literally had what? And I suppose the flurry of the question is, what does Pat Wheeler think? What is your idea of what the next gen batteries and what type of chemistry or materials are we looking at in next gen batteries? I mean, obviously people are talking about solid state. There's everything out there now. As an expert in the field, what do you think the next gen batteries are going to look like? What are we looking at from that chemistry point of view?
I'm probably going to dodge that question slightly. I'm an electrical engineer, not a chemist or a chemical engineer.
Fair.
There's a lot of technologies out there. There's a lot of things happening. Sodium always seems to come up, particularly in my university. There's a lot of different things that could happen. If you look at the research papers, you will find lots of people chasing research money to look at various different chemistries, all of which, if you believe the claims, will be fantastic. And it just takes one of those to succeed, in the same way that lithium did a few years ago. And I would hate to try and predict which one it will be. And if I knew, I'd be a very rich man, I suspect.
Fair enough. So let me phrase the question differently, Pat. Gen 2 battery, what are you going to put in your next bike?
At the moment, as we're developing electric vehicles, not just the bike, I've used the bike in this example, but we have a couple of cars as well. We tend to stick with lithium-based technology at the moment, but we tend to optimize the chemistries, not just to get the smallest, lightest battery we can, but to get the most suitable battery we can. So the battery pack on the motorbike isn't cooled; it just goes up in temperature. So it's just air cooled, if you like. And it's optimized for a particular temperature rise for a particular duty cycle. And by doing that, the system weight of the bike comes down, even though the battery is slightly higher in weight. And so there's still work and optimization to be done on the design at the system level. How do we get the best system rather than the smallest, lightest battery? And part of that is understanding use cases, understanding how to interact with the driver to get particular behaviors and so on. So this isn't all about the technology. There's a human being in the loop here as well. I can't help but sometimes wonder if that as we move to more automation in driving, particularly when we're driving long distances, if that might also be one of the key technologies to getting the most from electric vehicles.
The human element.
Yes,
100%. So Pat, you spoke about it briefly. Can you share one or two stories with us where you've pushed the technology to the breaking point and maybe a little bit beyond? I'm sure you've racing on the Isle of Man TT. Anyone who's gone racing has stories. Anything in particular that jumps to mind where you can say, this is where we really push the envelope, so to speak?
Well, we've done a lot of modelling of a lot of racetracks, not just the Isle of Man TT. There's a number of racetracks around the world where we know where every curb on every corner is. And part of the reason we did that was so that we can model the bike very accurately. So for the Isle of Man TT, for example, we know how the riders we've used will go around each corner, not just on the electric bike, but on an internal combustion engine bike. So we know the maximum speeds around various corners. And what that enables you to do is to build up the optimum lap to actually design the bike to do the speed you want around the whole course. That becomes really interesting because if you look at 2018, when we came second, we actually predicted the temperature rise in the battery to a maximum limit, which is the maximum limit just before the battery would burst into flames. And we were 0.1 of a degree centigrade away from that limit when we came over the finish line. So being able to have those models that predict how the technology is going to behave. Now, that's an extreme example on the Isle of Man TT, obviously.
Sure.
But if you take those techniques and that knowledge and you apply that to an electric vehicle, you can begin to see how you can optimize the vehicle, how you can feed information back to the driver so that he knows, where he's going to be able to stop. If he slows down by a couple of miles an hour, he's going to get to the next but one charging station rather than the next one. And actually his overall journey time could be shorter. So yes, we've been testing those modeling techniques out and we've been validating them in racing, great. But actually there are real everyday applications where you can use that to make the electric vehicle far more accurate in its predictions, far more interactive with the driver, so the driver can decide what he wants to do. Does he want to carry on driving at the speed he is, or does he want to slow down just that little bit and get to his destination 20 minutes earlier? All these things are quite possible, and the technology allows you to do that.
Fantastic.
We have had some incidents as well, not with our bike, thankfully, but people have pushed batteries too far. You begin to learn about fire suppression and all the rest of it through that as well. So people have learnt the lessons from racing and from making those mistakes, and that's also interesting in its own respect, because every time those incidents happen, you learn a lot more about how to do the engineering, what the important aspects are, and that de-risks the technology that we will be using on public roads. And I think that's an important aspect as well. Racing is a fairly safe environment to have things fail, and that just makes it safer for all of us as these vehicles begin to come onto the public roads.
Fantastic.
Yeah.
Divan, I know you've got a burning question now.
Absolutely. In terms of ICE vehicle production, there may be some unique elements in hotter climates like Africa and South Africa. So an OEM would have to have a different spec for Africa and South Africa. In your opinion, Pat, is there anything unique for electric vehicles, just due to our higher temperatures, higher local conditions, etc.?
Well, yeah, I'm familiar with this. I also do quite a bit of work in Chile, which in the north of Chile, they have the same problems. It's a very hot environment. Battery lifetime at the moment is very temperature dependent, and storage temperature as well as use temperature. So, you may have to, in hotter environments, you probably will need a cooling system for the battery packs. And you may want to think about how to keep the batteries at a good temperature when you've chosen to park your car in the sunshine on a very hot day. Things like that will have to be taken into consideration. They will affect the way you use your electric car, your electric vehicle. And they are aspects that you do have to take into account, in the same way as you take into account different environments when you design the cooling system of an internal combustion engine car. It's not, when you need to get heat out of a system, you do need to consider the environment that you'll be driving in. And they're challenging in different parts of the world. The added issue with the electric vehicles is that lifetime of the batteries due to that heat, even when it's just sitting there doing nothing. And that's something we'll need to take care of. Maybe a slightly more importance of parking your car in a shady space when it's not being used and so on.
Fantastic.
I can see that happening.
Well, Pat, I think we could chat more for a
Definitely.
while, but time has unfortunately caught up with us, and time's the one thing we never have enough of. So I think we're gonna have to love and leave you. And from myself and Devon in studio here in South Africa, thank you for taking time out in Nottingham to join us, and we'll be watching with bated breath in the next Isle of Man and seeing your e-bikes take on the internal combustion guys. But I think it's really been a pleasure for you to have you here explaining to all of us what is this technology that we're talking about. What is battery packs? What are we actually talking about, and making it into a way that the man on the street can understand the technology behind what we're talking about. So Pat, from myself and Devon here in studio in South Africa, thank you so much for taking some time out of your afternoon on Monday the 1st of March.
Okay, no, thank you very much. It's been a privilege to be here, and good luck with the rest of the conference. It's great.
Perfect, Pat. Thank you very much, and have a great rest of your day, sir.
Go well.
So that was Pat
brilliant.
Wheeler. I mean, you can see, incredibly smart guy, really knows everything, knows a lot about it, and talking about how he's taken motorbikes and use it as an opportunity to test the technology, find out when it's failed, find out when it doesn't fail, and then ultimately refine it so we can find that balance between weight, power, and I suppose what we're always looking for in electrification is efficiency.
Yes, and that's what it's about, and racing improves the breed. That's
100%.
that's the one thing I took away, and ultimately you've got to test, you've got to push, and up until the point where we get commercial.
Yeah.
We need these smart people to help us along to make sure that we got the right products at the right price.
Yeah, and I think it's really interesting how a gentleman like Pat, who's a professor, has lots of titles, PhD, he's got all the academic stuff, but he can explain it in such a way that I really hope people who are either watching now or watch later can understand these technologies that he's talking about. Can they say, okay, I understand why we need a battery management system, why we need this, why we need that, and how these systems are constantly being refined so that the vehicles that we eventually find one day on our roads are safe to use, and we can reliably use them in a way that allows us to be mobile, which as a human species is core to our existence, is to be mobile.
Yes, and fit for purpose.
Fit for purpose, 100%.
Absolutely, yeah.
No, and I think that. And I think that's been exciting. So what we're now going to change track just a little bit. Now we've got the background. We've spoken about green economy. We've spoken about everything. And really, with EMCSA, the design of the event has been talking about where we are. All our speakers this morning have talked about where we are currently. Now we're going to bring in a speaker, Anzette du Plessis, who is the Director of Proof Communications, and she's going to talk to us about convince us if you can. So convince us we can actually do this.
Right.
Because now this is where we are. We've spoken to both of the Buerta brothers, De Villiers and Yaku. They've outlined where we are. We've spoken to Anami. We've spoken to Pat. We've had all these conversations. We've had Daryl on from ESCOM. Everyone's given us a state of play as this is where we are in South Africa right now. Yes. Now we need to talk about how do we move forward, and how do we actually get to the technology and start this move forward to an EV movement. And I'm really, really excited to hear what Anzette has to say. And I think it's going to lead us nicely into day 2, where we can see what does the future hold? What can the future bring us in South Africa, and really make it of a local context?
Agreed. We need to convince ourselves first, and obviously then everybody else, and there we go step by step. And we need the right people with the right communication skills. We need the right platforms. We need to get the world now thinking around electric vehicles, the future of electric vehicles. What's the difference these cars are going to make into our lives, and how we travel, and how we get to it.
100%. I'm not sure. Anzette, are you with us? Are you online? All right, my apologies. We're just going to take a 3-minute break, and then we will have Anzette on with us. In 3 minutes' time, just give us a quick moment, and Anzette du Plessis from Proof Communications will be with us shortly.